Welcome everybody to our next lesson in grade 12U physics. So we've already reviewed motion graphs and we've already reviewed the kinematic equations. And we're going to start looking at acceleration and displacement in a little more detail. So far we've been limited mostly to one-dimensional movements, but hopefully you know that things often move in more than one dimension, and we're going to start looking at two dimensions. This is going to be really important a little bit later on when we move into things moving in circles, and more specifically circular orbits and things like that. So with that in mind, we want to do a little bit of work with this two-dimension idea. So the first thing we can do is talk about total displacements. And again, hopefully this is something you remember from grade 11, that a displacement is again, a movement from one location to another. And if we want to talk about something's total displacement, what we really need to be concerned about then is all the individual displacements and just summing them all up. So the total displacement would be equal to whatever the individual displacements are all added together. So in this case, delta d1 plus delta d2. So that means we do have to add vectors since displacement is a vector. So remember, for instance, down here, we're looking at an example with a person traveling 56 kilometers north and then 42 kilometers east. Remember, we can't just add those up and get 98 kilometers and say that's our displacement. That would actually be the total distance traveled by this person. But again, we're looking for the displacement, which is the pretty much just looking from the start point to the end point. What is their change in their position? So remember, when we're adding, no matter any vector of any kind, you're always going to add it in the same manner, which is tip to tail. And what that means is wherever one vector ends, the other vector must start. And again, it makes sense if you think about displacements, because when you walk, you start your second motion where your first motion ended. So let's draw our attention now to this example. So what we have is this person traveling 56 kilometers north and then 42 kilometers east. And I want to know, what is this person's total displacement? So really I need to add this vector, 56 kilometers north, to this vector, 42 kilometers east. I just realized perhaps I should make sure I put on my compass rose just to indicate where we are, but I think we're safe to assume that we're in the standard sort of reference where north is up. So what we need to do then is add this vector, 56 kilometers, to this vector, 42 kilometers. And again, we add the second vector where the first one ends. So we want to kind of connect them up like this. And then what we want for our final displacement, our total displacement, is the change in position from where it started to where it ended. So really, again, what I'm looking for in this case is this what we call the resultant vector, which is just this vector right here. Remember that in order to describe a vector, you need to tell me its magnitude or size and the direction that it's heading. So what that means is I need to measure this angle here, we'll call it theta, and I need to measure the length of this red arrow. Hopefully, again, you can see this is a nice right angle triangle. Right angle triangle lends itself very nicely to the trig ratios. And I'm not going to go through it with you, but hopefully you can get it on your own. And if not, again, of course, let me know. But that means this red vector is 70 kilometers long. And this angle turns out to be 37 degrees. And the way I'm going to state that angle is going to be north 37 degrees towards the east, because I think that makes sense. It's like you start heading, oops, not west. You start heading or pointing your vector towards the north, but then you actually swing it over 37 degrees towards the east. Notice an equivalent way to say this vector, we could actually do I think that's complementary angles, and say that's then going to be 43 degrees. Oh, pardon me, 53 degrees. So an equivalent way to state that same direction would be east 53 degrees north, which is just saying now I'm going to start east and head 53 degrees towards the north side. In either case, there's our resultant vector. This is the displacement of this person during their walk. Okay, so there's the first example, pretty straightforward. Hopefully, again, stuff you remember from doing in grade 11. Now into something a little more complicated. Just in terms of math, the physics behind it is identical, but now we have to do a little more math skills to do this. So we have this airplane, it's traveling 56 kilometers north, so this vector right here, and then it's going to travel 260 kilometers north, 26 degrees east. So I've again labeled that vector for you here, and I want to know the total displacement. So again, I want to know from this starting to start the next vector, and then where this ends. So once again, I want the resultant or total displacement, and so I want to know this vector. So I said again, the physics is identical, but the math is a little different. The only problem here is this isn't a right angle triangle, so we can't just use our basic SOHCAHTOA methods. Um, the two kind of ways that spring to my mind are the cosine law, which certainly would work in this case, but the method I'm going to encourage you to use, and again, hopefully you'll see why in a couple weeks when we get there, but is to use the component method. And all that means is for any vector that's not along one of our directions we picked, like north, east, south, or west, or we could say like up or down or left or right for other kind of problems, it's breaking that vector, so this 26 or 260 kilometers at 26 degrees, into two perpendicular vectors that would summarize the same vector. And what I mean by that is, let me pull this one over here. I want to break this vector into two other vectors, one that is strictly north, and add to it another vector that is strictly east. So kind of like that. And when I do that, I hope you can see that the blue one and the green one together will be equivalent to this black one, which means if I want to add that vector, oh my goodness, look at that, it fits nearly perfectly. So all we have to do then to solve this problem is use now SOHCAHTOA, or our three basic trig ratios, to find the length of these sides. I've done that. Oh, that's too big. And I found those. Again, hopefully you can follow along and do those calculations on your own if you're interested. But I found that to be 114 kilometers east. So for that vector there, and the vertical vector is 234 kilometers. So now what we have, if I put these up here, let's get them all together again. It's like we have three vectors we're adding, but now they're all at right angles. So adding these two together would be simple because it's just taking the total distance here. So this whole north section will just be, what is that, 794 kilometers. And the top section is still 114. So really, that's all we have to worry about then. So this one section here is 794. So now we've broken our problem, which had to be used by, or was not able to be solved by the simple trig ratios with the simple trig ratios, because we have a vector that's 794 kilometers north and 114 kilometers east. So again, I won't bore you with the details here, but the answer that I got was 802 kilometers. And then I got that angle to be 8.2 degrees, this one right here. So the way I'd state that is north, 8.2 degrees east. So that's what I got, and hopefully, again, you can verify that and get the same one. Okay, so that's that kind of get it for displacement. So really, those are the only kinds of problems I can ask you. The only way to make it really harder is to add more vectors, but the process will always be the same. Break those down into perpendicular vectors called components, and then just plug and play and use your simple trig ratios. So if we turn our attention now to acceleration for a minute, remember that acceleration is defined as the change in an object's velocity divided by the change in time and how long it took to make that change in velocity. So the one thing that sometimes confuses people, notice this is not speed, it's velocity. And so what that means is if we imagine a car, let's say, turning at a constant speed, maybe a left-hand turn out of a plaza or something, even if it's at a constant speed, it's still accelerating. We know that because velocity is changing. And again, this will become important later on when we talk about forces, because remember, anytime there's an acceleration, there's a force involved. All right, so now we have to actually worry about subtracting two vectors, though. And you might say, well, Mr. Young, I don't remember ever learning how to subtract vectors, and you maybe never did, but it's not terribly difficult. To subtract two vectors, all we have to do is add the negative. So let me give you an example to kind of explain that. So let's consider a car traveling 10 meters a second east. So it's heading this way, and then it turns, so it's now going 10 meters a second south. So of course, it's probably going to be more of a turn, a circle, as opposed to a 90-degree turn, but it doesn't matter because we're only interested in these final velocity and initial velocity vectors. And it takes 2.5 seconds to do that motion. So again, hopefully you can see it's pretty easy to set up this equation. It's just going to be 10 meters a second south minus 10 meters a second east divided by 2.5 seconds for the average acceleration, just based on our equation for acceleration. So again, I've drawn these vectors for you here in a little nicer form. So I have 10 meters a second east, and I need to subtract 10 meters a second south. And as I said, in order to do that, all you really have to do is subtract the negative. And I think we had this discussion in class the other day. But when we talk about negative south, all that really means is north. So instead of subtracting this vector, all I need to do is add this vector. It's just the exact same length, but pointed in the opposite direction. And now it's going to reduce to a problem, hopefully, again, is easy to solve here, because all we're doing is adding two vectors that are now, oh, fine, that are adding two vectors that are at right angles to each other. So I don't like that one vector there. Let me get rid of that guy. Nope, not going to happen. Oh, and I know why. I'm going to backpedal a little bit here. Hopefully I don't confuse you guys too much because I went way too fast here. We're looking at the final velocity minus the initial velocity. So it's actually this vector, 10 meters a second south, minus this vector, 10 meters a second east. My apologies there. So instead of worrying about this vector being the negative, it's this vector the negative. But it's still the same process. So instead of 10 meters a second east, we're talking about negative 10 meters a second east, or 10 meters a second west. So now all we have to do is add these two vectors. Come on. Add these two vectors together. Hopefully, again, you can see that's pretty easy. So I've summarized it sort of here for you. This is what we've done. We said the acceleration is 10 meters a second south, take away 10 meters a second east, which is really adding negative 10 meters a second east, or adding 10 meters a second west. So again, we've now resolved this problem to a fairly simple trigonometric problem. And again, I won't bore you with the details here, but I got for my answer, where am I here? 5.7 meters per second squared. And the directionality, notice this is 10 and 10, so this angle here will be 45. And so I can just then say south 45 degrees west, pardon me. So hopefully, again, that makes sense, and I'd like you to verify that, make sure you get this, but I think it's, once you realize we're adding the negative, it should be pretty straightforward. And I have one last example for you before I'm done today. And this one has to deal with the same situation, but again, notice we have a vector that's not traveling in a perpendicular direction, not exactly north or south. So here's this boat traveling at 22 meters a second. Here is the initial velocity at an angle of west. Oops, that's not 26. That should be 30. 30 degrees south. So that vector there. And then the other one is going to be 14 meters per second. So it's traveling from this velocity to this velocity. So it's like we're heading this way, and then all of a sudden the boat swings to the right or to the north, and this is our final velocity. And again, I want to know the average acceleration. So I've set up again this kind of step-by-step equation for you over here on the right-hand side. And notice the negative of this vector is just this vector. Exactly the same length, still 22 meters a second. I did the 26 again, pardon me there. But now it's pointing in the opposite direction. So instead of going west 30 degrees south, it's now going east 30 degrees north. So notice kind of the parallel here, right? So it was west 30 degrees south, and now it's east 30 degrees north. It's almost like we just flipped both of those directions. We're turning that vector around. So now it's just a matter of adding these two vectors together, because we're going to add 14 meters a second west plus 22 meters per second east 30 degrees north. So we're just going to add this vector to this vector. And you might say, okay, well, now we're almost doubling back on ourselves, and we are, so we have to be careful. But we're going to do the same process. We're going to break this vector into its perpendicular components. So again, a vector that's pointing straight east added to a vector that's pointing straight north. And then we want to resolve that into components and figure what that is. So again, I've already done that ahead of time, and I have, for my answer, so the north vector is actually broken down into 11 meters per second, and the east vector was broken down into 19 meters a second. So if we imagine we have this now, and we're just going to add this vector here to this vector. So notice we've gone 14 this way and 19 this way. So 14 west, 19 east, which means we've really only gone 5 meters a second east and then 11 meters a second north. So again, I can resolve this whole problem into something just like this. So here's my two vectors. So this one is going to be 5 meters a second, and this one's going to be 11. And lo and behold, we once again have a right angle triangle, which means we can use our simple trig ratios to solve. Um, but again, the cosine law would have worked, but I think in the long run, this will be something better for you. And I'll leave this one for you to do again, but the answer I got after I've calculated the acceleration is 0.19 meters per second squared. And of course, the direction we've already talked about. So I got, in this case, east 66 degrees north. Okay, there we go. So again, let me know if any of these questions you have trouble repeating what I've done or you're confused with explanations. But I think for the most part, if you're okay with the stuff from grade 11 and you're okay with vectors, then this shouldn't be a problem for you. Okay, I look forward to seeing everybody in class.